Hi, everyone, and welcome back to part two of creating a weather app using Jetpack Compose and Clean architecture. Here's a quick recap of what we did in part one. We started with our data module, where we created our repository, set up Firebase and maps, and finally integrated retrofit with our API service class. In this part, we'll be completing our domain module, creating an onboarding journey with manual and automatic location selection, and building a settings screen. We'll also look at how to implement permissions, use the new Navigation 3 library, and animate maps. So stay tuned and let's get our hands on the code. So let's get started. We'll begin by creating the domain module. To do this, right-click on the project, choose New Module, select Android Library, and name it Domain. In a production environment, you might prefer a pure Kotlin library here, since the domain layer should ideally remain platform independent, but using an Android library works fine for our setup and makes it easier to follow along. Inside this new module, we'll add three packages: model, repository, and use case. Think of the model package as the home for all of our pure Kotlin data classes. The repository package will hold only the interfaces that describe what data operations are possible. And the use case package will define the specific business actions, such as getting the weather or fetching health recommendations. This structure keeps responsibilities clear and makes the code easier to test and maintain later on. Next, we'll enable type-safe project accessors at the root of our project in the settings file. This Gradle feature lets us access modules as typed properties instead of plain strings. It might sound small, but it gives us IDE autocomplete, reduces typos, and just makes the overall development process smoother. Once that's in place, we'll go to the data module and add domain module as a dependency. This follows an important clean architecture principle. The data layer depends on the domain layer, not the other way around. By keeping this direction of dependency, our business logic stays independent and reusable. Now let's head back into the domain module. Inside the repository package, we'll create sub-packages for app, database, Firebase, places, and weather. These match the data sources we plan to work with, but remember, here we're only adding the contracts, the interfaces. After that, we'll move the repository interfaces we built in the data module during the last video into their correct packages in the domain module. The reason for this move is that in clean architecture, the domain layer owns the interfaces and the data layer implements them. That's what makes it possible to change or swap out a data source without rewriting our core logic. Since the last video, there are a couple of updates to mention. First, we've updated some of the dependencies, and you can always find the latest versions in the GitHub gist linked below. Second, the structure of the AQI health recommendation response has changed slightly. Now the API gives us the first key AQI index, followed by a title, a description, and a list of health recommendations. These recommendations are grouped by audience, like the general public or sensitive groups, so it's easier for us to display accurate information in the app. Finally, you might remember that in the previous part, we created a temporary package with some placeholder model classes. Now it's time to clean that up and move those models into their proper places inside the domain layer. Next, we'll move into the data module and create a new package called mapper. Inside it, let's add a file named locationext. The purpose of this file is to handle the conversion between our domain models and our local database entities. Here you can see two extension functions. The first one takes a location model, which lives in the domain layer, and converts it into a location entity, which is the room database representation. The second function does the reverse. It converts a location entity from the database back into a location model for the domain layer. Now let's complete the user settings model class. This class represents the preferences and app configuration chosen by the user. At the top, we define three enums. The first one, units, lets the user pick between metric and imperial systems for weather data. The second, appearance, controls how the app looks, whether it follows the system default or is forced to light or dark mode. The third, onboarding status, tracks where the user is in the onboarding flow, starting from the welcome screen, moving through location setup, and finally marking it as complete. With those enums in place, we create the user settings data class itself. It ties everything together. After that, We'll write out the Aki model class. This model represents health recommendations for different groups of people based on the air quality index. Next, let's look at the weather forecast model. This data class represents the complete weather forecast that will display in the app. At the top, it holds basic information like the location and whether it's currently day or night. Then we have the current weather condition, which includes the actual temperature, the feels like temperature, a short description of the condition, such as cloudy or sunny, and the icon code that we can use to display the correct weather symbol in the UI. Following that, the model contains a list of hourly stats. This is a nested data class that captures the weather details for each hour of the day. For every hour, we will store the time, its epoch value for precise calculations, the temperature, the icon code, and the chances of rain or snow. The model also tracks humidity and dew point, which give us a sense of air moisture levels, along with pressure and its unit. We also include air quality. Finally, the model holds astronomy data like sunrise and sunset times, moonrise, and moonset. The weekly weather forecast model represents weather data for an entire week, split into hourly and daily sections. The hourly data map links a time string to an hourly forecast, which includes details like temperature, humidity, rain, wind, and a weather code to describe conditions. The daily data map links a timestamp to a daily forecast, which summarizes the day with max and min temperatures, wind, sunrise, and other details. Hourly forecast gives fine-grained detail for each hour, while daily forecast captures the bigger picture for each day. Previously, our user settings repository methods used plain strings, but now we've replaced them with proper types like units, appearance, and onboarding status. This makes the code type safe and avoids errors. Notification settings stay as simple booleans. We've also added user settings flow, a state flow that continuously emits the latest user settings, so the UI can react automatically whenever preferences change. Now we'll update the repository implementation to match the new strongly typed API. We added an init block that loads settings into a mutable state flow, so the UI always has the latest values. Each save method now writes to DataStore and refreshes the flow, making the UI react automatically. Enums are stored as strings, booleans as flags, and keys are centralized. The flow is exposed read-only with as StateFlow. Finally, we update the database repository to use the mapping extensions we created earlier. Instead of directly working with entities in the repository, each method now calls to entity when saving and to location model when reading. We'll complete the use cases starting with autocomplete places use case. This one acts as a simple focused entry point for place suggestions. It takes the user's free text query and delegates it to the places repository to fetch a list of place suggestion results. Next is fetch full detail for place ID use case. After a user taps a suggestion, we need the precise coordinates and richer details for that place. This use case accepts a place suggestion, asks the places repository for its latitude and longitude by place ID, then maps those details into a location model that our domain layer understands. Then we add save location use case, which takes a location model and persists it via the database repository. The intent here is deliberately narrow. One responsibility, insert the given location and mark it as current. Finally, save location with latlang use case covers the scenario where we already have raw coordinates along with city, area, and country names. It constructs a location model on the fly, flags it as current, and delegates to the database repository to insert and set it active. We'll also create the user settings use cases to keep the UI thin and the logic consistent. Get user settings use case exposes a reactive stream of settings by returning the repository's user settings flow. Save appearance use case delegates the user's theme choice to the repository. Save onboarding status use case does the same for onboarding progress, ensuring the app can advance through the flow and persist that state reliably. Save units use case updates the measurement system to metric or imperial, so all downstream weather formatting stays consistent. Update daily notification use case toggles the daily forecast notifications. Update severe notification use case controls severe weather alerts. Grouping these as small, single responsibility use cases makes testing straightforward. Before jumping into the onboarding screen, let's create a new module called UI Kit. the same way we created the domain module. This module will hold our reusable Jetpack Compose components so we can keep the app screens lean and consistent. Later, we'll even be able to publish it as a standalone library on Jetpack for future projects. For this project, we'll start with 3 components and set up the packages accordingly: a common app text for typography, an app button for call to action moments, and a dot indicator for paged or onboarding screens. We'll start with app text. Default app font family provides a default font sans serif. Custom font families is a data class that lets you define both a default font and, optionally, a custom brand font. Local app font families is a composition local, which means you can provide and override font families anywhere in your Compose hierarchy. This makes it easy to swance at runtime or for specific parts of the app. Text type is an enum that categorizes all the standard material typography roles: display, headline, title, body, and label, each in multiple sizes. These follow the Material 3 guidelines so you can style text consistently. The app typography object holds all the text styles. Inside, styles is a private map that links each text type to a text style. The first initialize function builds this map using either the brand font, if available, or the default font, and applies the appropriate weights and sizes for each category. These numbers, like 57 SP for display large, come directly from Material 3's recommended scale. There's also an overloaded initialize function that lets you inject a completely custom map if you want. GetStyle is a composable function that looks up a text style for a given text type. If nothing is found, it falls back to textstyle.default. In short, app typography centralizes all your text styles so you don't hardcode sizes or weights in individual composables. Finally, you create your reusable text component. It takes in a string and optional parameters like color, alignment, overflow behavior, and max lines. By default, it uses the body medium style. It fetches the correct text style from app typography and passes everything into Jetpack Compose's built-in text. We're setting up a flexible, future-proof CTA system for buttons by first defining what kind of content a button holds and how it should look. Button kind tells us whether the component renders text or an icon, while button type captures the visual treatment in material terms like filled, tonal, elevated, outlined, and a lightweight standard text style. Sizing comes next. Button size encodes height and horizontal padding for 5 tiers, from extra small to extra large, so spacing stays consistent across the app. A helper function returns a corner radius per size, which keeps the shape proportional to scale. That way, tiny buttons don't look overly rounded and large buttons don't feel too sharp. With size and type defined, button variant ties everything together in a single sealed hierarchy. Each object represents a valid, pre-approved combination of kind, type, and size, like a filled medium text button or a tonal icon small icon button. Because it's sealed, you get exhaustive handling and prevent invalid mixes at compile time. It also makes call sites clean and self-documenting. You pick one variant and all 3 dimensions are resolved. This reduces boilerplate and avoids styling drift. Shape control is modeled with button shape preset, a sealed interface that offers sensible defaults: full rounded small corners, square, and round, plus a custom option for exact radii. Finally, app button style is a compact style contract that a button can read at render time. It specifies which text style to use from your typography system, the base shape, and optional shapes for pressed and selected states to support subtle state transitions. It also carries a mutable interaction source, so the button can react to user input consistently. Now let's look at the flexible app button that adapts to both text and icon use cases. We start with a clean set of parameters: optional text, a click handler, a variant that bundles kind type size, optional leading and trailing icons, an enabled flag, a toggle to make it full width, and a style object that carries typography, shape presets, and a shared interaction source. Right away, we listen to user input by collecting the pressed state from the interaction source, so the button reacts instantly to touches. We also keep a selected flag ready for future selection behavior. With those 2 states in hand, we decide which shape preset to use. From that preset, we compute the target corner radius using shortcuts for fully round and square presets, and then animate it with animate DPA state. This gives the button a smooth, polished shape transition on press or selection. Next, we unpack the variant into its size, type, and kind, and apply consistent height and optional full width layout. We also derive horizontal padding from the size, so spacing scales naturally across extra small to extra large buttons. For the content, we build a simple row, an optional leading icon, the text rendered through app text using the configured typography, and an optional trailing icon with standard icon size and spacing to keep everything aligned. Now we branch by kind. If this is a text button, we choose the correct material composable based on the type. Filled and tonal use their material counterparts with explicit colors from the theme's color scheme, so primary and secondary roles are obvious. Elevated, outlined, and standard text button use their material defaults while still inheriting the animated shape, consistent padding, the shared interaction source, and the same content we prepared. If this is an icon-only button, we create a square hit target based on height, render just a single icon, and switch among filled icon button, filled tonal icon button, outlined icon button, or the standard icon button. Again, we apply the animated shape and theme-aware colors for filled and tonal. The result is one entry point that enforces consistent sizing, spacing, and motion across all CTAs, while keeping the UI expressive with variance. Next, we're building a reusable dots indicator that's perfect for onboarding flows or any paged UI. The function takes 4 parameters: how many dots in total, which one is currently selected, and the 2 colors that distinguish selected from unselected states. Inside, we use a lazy row because it lays out items horizontally and efficiently, even though the number of dots is usually small. We add wrap content width and wrap content height, so the row takes just enough space, and animate content size, so if the content changes, the transition feels smooth instead of jumping. For each index, we decide whether it's the selected one. If it is, we draw a box that's slightly pill-shaped by clipping it with a rounded corner and filling it with the selected color. If it's not selected, we draw a rectangular box with the unselected color. Last, we insert a spacer with horizontal padding so there's even spacing between indicators. Let's head back to our app module. Start by creating a new D package and adding a presentation module. We mark the module for Hilt with the standard annotation so it's installed in the application-wide graph. That way, these objects are available across the entire app. Inside, we provide a Fuse Location Provider client, Google Play Services High Accuracy Location Client. It needs the application context to bind correctly. Next, we expose a location helper as a singleton. Think of this as a thin wrapper that centralizes permission checks and retrieves the last known location. Finally, we provide a Places client from the Places SDK. If Places isn't initialized, we initialize it once with your key from build config places key, and then create the client. Now let's add a couple of project-specific UI pieces. First up is the maps composable. We read the current context, pick a map style based on whether the system is in dark theme, and render a Google map that fills the screen. We feed it a camera position state, which you'll usually hoist to the view model so camera moves survive recomposition. For this screen, we disable zoom, rotation, and scroll gestures. This keeps the map purely presentational so the user isn't fighting accidental pans while reading weather. For styling, we load a raw JSON style from resources and pass it as a map style options. This lets the map match the app theme exactly in both light and dark modes. When you want to apply a custom look to your maps, start in the Google Cloud Console. Search for Maps SDK for Android, then open the Map Style section. This takes you to the styling editor where you can adjust the appearance of roads, landmarks, water, or even hide features entirely. You'll see 2 options. Pick from Google's preset styles or export a JSON file with your own configuration. Once you've customized it, download the JSON and place it in your project's assets folder so it ships with your app. In the Maps composable, load it with mapstyleoptions.loadRaw resource style or from assets if you prefer. This way, your map matches your brand identity and supports both light and dark variants without hard coding. Next is the show dialog composable for permissions and simple confirmations. Here we use alert dialog with onDismiss request funneled to a single onDismiss lambda so the caller controls lifecycle. Titles and messages come from string resource, and we format text through app text so typography stays consistent with our design system. The confirm button uses app button with a text variant. When permission denied is true, we change the label to grant permission, and on click, open the app's settings screen so the user can enable permissions, then dismiss the dialog. Otherwise, the confirmation just acts as a plain OK. We also add a dismiss button that always calls on dismiss. All right, intro done. Let's get started with our onboarding screen. Inside the feature package, create sub-packages for location, onboarding, settings, and web. For this video, we'll focus on onboarding. Here we start with a component specific to the onboarding journey, the sun moon animation, built with a custom canvas. We add a tiny helper that converts degrees to radians, keeping our trigonometry readable. The composable takes the current pager page and swipe offset, and together they form a continuous progress value that drives smooth animation across pages. We grab local window info to read the container size, so all positions are computed in pixels relative to the screen. From that, we derive a center X, a left anchor, a top anchor for the arc apex, and a bottom anchor near the lower edge. This ensures the sun and moon travel along a pleasing semicircle instead of hugging the edges. Inside the canvas, we calculate total progress as page plus offset and drive 3 phases. Phase 1, from page 0 to 1, the sun rises along a semicircular arc. We interpolate an angle from 180 to 0 degrees, then use cosine for x and sine for y, which draws a left to right sunrise peaking at the top anchor. During this phase, the moon stays hidden. Phase 2, from page 1 to 2, we crossfade the bodies. The sun sets by moving downward and fading out, while the moon rises from the opposite side using mirrored trigonometry. We ramp the moon's alpha up so it feels like a handoff. Phase 3. After page 2, the scene settles with the moon fixed at the apex and the sun fully off-screen. We then render both bodies as circles, the sun in warm yellow, the moon in cool light gray. Their size comes from a DP value converted to pixels, so they stay crisp at any density. Finally, alpha checks ensure we only draw what should be visible in each phase. This avoids overdraw and keeps the transition clean. We're building a simple, reusable piece of the onboarding flow, the intro text block. The composable takes in a title and a description, so each onboarding page can supply its own copy. We use a column that fills the width and centers its children horizontally. This keeps the text aligned neatly in the middle of the screen, regardless of device size. Inside, the first app text renders the title. Right below it, another app text shows the description using body medium, a more readable body style. Next, create a package named Welcome inside the onboarding package. We're wiring the onboarding flow with a simple state and effect pattern, then rendering it with a pager and the sun-moon backdrop we built earlier. First, we define a lightweight effect marker, navigate to next screen, which represents a one-off navigation event. Alongside that, State holds a list of onboarding pages, and each onboarding page model stores the string resource IDs for the title and description. In the ViewModel, annotated with @Hilt ViewModel, we inject save onboarding status use case so the business logic for persisting progress stays out of the UI. A private mutable StateFlow backs a public StateFlow to expose read-only state to the screen. For one-shot actions, we use a mutable shared flow and expose it as a shared flow. This is a clean way to model navigation or toasts without risking duplication on configuration changes. During init, we populate the page list with 3 items sourced from strings.xml. When onboarding is complete, onboarding complete launches a coroutine, saves the status through the use case, then emits the navigation effect so the UI can react. The onboarding screen composable grabs the view model with Hilt view model, then collects the effect inside a launched effect block. This is the typical pattern for handling one-off events in Compose. Side effects are collected in a coroutine tied to the composition, and when navigate to next screen arrives, we call the onNext callback passed in from the host screen. We also collect the state, create a pager state, whose page count is driven by the list size, and hand everything to onboarding container. The click dispatcher we pass simply calls onboarding complete with the next logical status, location, so the flow advances and persists. Inside onboarding container, we read the page index and offset from pager state, then layer the UI. A surface-colored box hosts the animated sky, while a horizontal pager displays full-screen background images. At the bottom, a column centers the intro text, progress dots, and on the last page, an animated continue button. Here's a quick overview of how it looks on the device. Location helper is a utility class that fetches the user's last known location using Fuse Location Provider client with a 10-second timeout. It then uses geocoder to convert the latitude and longitude into a human-readable address, returning the result safely with run catching. This code defines two sealed interfaces, UI effect and UI event, which group together all possible one-off effects and user-driven events for the location flow. Using sealed types ensures exhaustiveness in when statements, making the UI logic safer and easier to maintain. This view model coordinates the onboarding location step. It listens for UI events, triggers one-off UI effects like navigation or permission requests, and when permission is granted, fetches the last known location. Get last known location launches a coroutine, asks location helper for the user's address, and handles the result with fold. If successful, it extracts latitude, longitude, city, area, and country from the address, saves them through save location with latlang use case, marks onboarding as complete, and finally emits a navigation effect to move to the main screen. Next is the composable for the onboarding preference screen, where the user chooses how to set their location. It wires up the onboarding location view model, listens to its effect flow with launched effect, and reacts by navigating, requesting permissions, or showing a dialog when permission is denied. A permission launcher handles the runtime request for fine location access. The UI itself shows a map in the background with a card at the bottom containing the location selection options, ensuring everything is consistent with the onboarding flow. The container composable lays out the content inside this bottom card. It starts with a title and a short message explaining location setup, both styled through the app's typography system. Below that, two buttons give the user options, one to search for a location manually and one to fetch the current location via GPS. Each button triggers the corresponding UI event back to the view model. For location, let's create a few components first. Location Suggestions List is a composable that shows search results in a drop-down style list. If there are suggestions, it renders them inside a lazy column, with each item clickable through on suggestion click, and adds a divider between items for clarity. If no results are available but the search field is expanded and non-empty, it shows a helpful message, either asking for more characters if the query is too short or saying no suggestions were found. Suggestion item is a composable that displays a single suggestion row. It uses a row layout with spacing and padding, making the whole row clickable via the onClick callback. Inside, it shows a location pin icon followed by the city name in a larger text style and the country name in a smaller text style. Selected Location Card is a composable that highlights the city a user has chosen manually. It's wrapped in a rounded card with a slight elevation for emphasis. Inside, a column lays out three elements: a large headline showing the city name with a weather emoji, a short description text, and a full-width button labeled Select this location. Tapping the button triggers the on-save location callback, allowing the app to confirm and save the chosen city. We're defining the MVI contract for the manual location screen. There's a single effect that represents one-off navigation to the main screen after a successful save. Events capture all user intents in this flow: typing a query, canceling search, choosing a suggestion, and confirming a selected location. State models the UI at 3 points: the initial input field with an optional query, a suggestions list when results are available, and a committed selection with the chosen location. Manual Location View Model manages the logic for the manual location step. It uses the 4 injected use cases we created earlier. The event function is the heart of the view model. It reacts to incoming UI events, updates UI state, or triggers UI effects. Manual Location Search Screen is the composable that drives the flow. It wires the view model to the UI, collects its UI state, and reacts to UI effects. Locally, it manages the search field state, the current query, whether the bar is expanded, the live list of suggestions, and any location the user selects. A camera position state is remembered to control the map, and when the user picks a location, the camera animates to those coordinates. The search bar handles typing, clearing, and submitting. Typing is debounced, and once the minimum character length is met, the Get Manual Location event is sent to the view model. Suggestions appear in a drop-down, and selecting one dispatches Select Location. If a location has been chosen, a selected location card appears at the bottom with a Confirm button. Pressing it sends save selected location, which persists the choice and completes onboarding. Colpic handle search debounce prevents firing API calls on every keystroke. It waits half a second after the user stops typing, then triggers a search only if the query still matches the text field. If the field is cleared, it cancels the search. Handle UI state updates observes UI state changes from the view model and routes them to the right callbacks, updating suggestions, animating the map to a selected location, or clearing results when search resets. Animate map to location smoothly moves the camera to the chosen coordinates, adding a small delay so the transition feels natural. Location search bar wraps Material 3's search bar and plugs into the app design system. It manages query changes, submissions, and expanded state. It shows a hint with the minimum character requirement, a map pin leading icon, and a clear button when text is entered. All right, let's move to the settings screens. Before that, we'll add a few handy extension functions for app settings, store access, sharing, and notification checks. Open app settings on activity opens the system's app details screen so the user can adjust permissions or clear data. Open Play Store on context opens the app's Play Store page, preferring the Play Store app and falling back to a browser. Share app on context creates a share intent with a short message and your Play Store link. Are notifications disabled on context returns true if system notifications are turned off for the app. Setting item type toggle is a composable for a single settings row with a switch. Title and optional subtitle sit on the left. A switch sits on the right. The checked state controls the toggle, and on-check change lets the parent persist changes. Item segment selector creates a segmented control where users pick one option from a row. It shows a title, then a single choice segmented button row. Each button highlights when selected, updates selected index, and calls back so the parent can react. Setting list item represents a navigable row. On the left, it stacks a title and optional subtitle. On the right, a lightly transparent rotated arrow indicates navigation. A row with a spacer keeps the layout clean and aligned. Setting actions is a sealed interface that represents every possible user action on the settings screen. Each object corresponds to a specific interaction, like changing units, toggling notifications, or opening links such as privacy policy, release notes, or credits. Using a sealed interface keeps all actions type safe and ensures they're exhaustively handled in the view model. Setting list view type is a sealed interface that defines the different types of items shown in the settings list. Segment selector represents a row with multiple options, like units or appearance, where one can be selected, while accordion section represents a collapsible row with a title, subtitle, and an optional action, like privacy policy or share. This structure keeps the settings UI flexible and type safe. Setting list view type models the two kinds of UI elements in the settings screen. Generate settings list builds the structured list of settings sections based on the current user settings. It creates a block for units and appearance using segment selector, then adds a notifications section that adapts dynamically. If system notifications are disabled, it shows an accordion prompting the user to enable them. Otherwise, it shows toggles for severe alerts and daily forecasts. After that, it adds a social section with share with friends and rate us, followed by an about section containing version info, privacy policy, and credits. The helper to int value converts booleans into indexes for the on-off selectors, making the mapping straightforward for the UI. This design keeps the settings screen modular, reactive, and easy to extend. This contract defines how the settings screen communicates with its view model. UI event captures all user and system actions, like changing a setting, starting the screen with current permissions, or handling notification permission results. UI effect represents one-off side effects such as navigation, sharing, rating, or scheduling notifications that shouldn't live in state. UI state holds the renderable data, a list of settings item model, so the UI can simply display the latest settings while all interactions flow back as events and effects in a predictable unidirectional way. Setting view model drives the settings screen with a simple MVI loop. It exposes a state flow of UI state for rendering and a shared flow of UI effect for one-off actions. On onStart, it collects get user settings use case and rebuilds the screen with generate settings list, passing whether notifications are currently disabled at the system level. When the user changes a setting, the event function routes by action. Save appearance or units via their use cases. Toggle daily and severe alerts via their use cases. Emit effects for share, rate us, privacy, credits, or scheduling canceling notifications. If notification permission is granted, it enables both alert types. A small handle helper centralizes effect emission, so intent stays clear and the code is easy to test. Settings screen wires the settings UI to its view model and handles notification permission on Android 13 and higher. It registers a permission launcher for post notifications, forwarding the result to the view model as granted or denied, along with the correct rationale flag. On start, it reports whether app notifications are disabled at the system level. It then collects one-off, on-off effects to act on. The UI itself renders the current settings via setting list, and any user interaction is dispatched back as on-setting item change. Setting list lays out the entire settings screen as a scrollable list. It begins with a screen title, then iterates through each settings item model group and lays out its sections. Topic: Local web screen is a composable for showing local web content inside the app. It uses Android View to embed a native WebView into Compose, stretches it to fill the screen, and enables DOM storage so modern pages work correctly. The file route parameter is passed directly to load URL, letting you open bundled HTML files or local assets, such as release notes, privacy policy, or credits, without leaving the app. Activity View Model controls the app's startup flow and theme selection. It starts with the onboarding screen as the default destination and a loading state set to true. In the init block, it collects the user settings flow from the repository. Based on onboarding status, it updates the start destination. At the same time, it applies the saved appearance theme. After a short delay to smooth the transition, it marks loading as complete. This ensures the app launches into the correct screen with the right theme every time. Destination defines all possible screens in your app using a sealed interface, keeping navigation type safe and exhaustive. Each destination declares a screen name for identification and a screen function to render the corresponding composable while receiving the backstack. A nested onboarding journey groups the onboarding flow into two steps, the intro screen and the location selector. Each step pushes the next destination onto the backstack when complete. Other objects represent independent screens like manual location search, settings, and local web pages. This keeps navigation centralized and easy to maintain. Finally, main activity is the entry point that wires everything together. It installs the splash screen and keeps it visible until the activity view model finishes loading user settings. It enables edge-to-edge drawing for modern UI and initializes the Google Places SDK with your API key. Inside set content, it observes the saved theme and applies it through Weatherwise theme. A scaffold provides the base layout, while a box hosts the navigation system. Navigation starts from the destination chosen by the view model and is managed through a simple backstack. Each destination renders its composable through nav display and nav entry, giving you a type-safe, compose-first navigation flow. All right, we've set up navigation, connected the view model, and initialized everything from onboarding through settings. Let's run the app and see it in action. Thanks so much for watching. If you found this helpful, don't forget to like the video and subscribe so you won't miss the next part. In the upcoming video, we'll wrap things up by building out the weather screens and bringing the whole experience together.